Today we are going to learn about optimizing TensorFlow model loading for production. This video will teach you how to efficiently load TensorFlow models in various production environments, ensuring responsive and scalable AI solutions.
Welcome to our video on optimizing TensorFlow model loading for production environments. In this video, you'll learn how to efficiently manage TensorFlow models to ensure that your AI solutions are both responsive and scalable. We'll cover everything from the basics of the TensorFlow SavedModel format to advanced techniques like lazy loading and TensorFlow Lite. By the end of this session, you'll be well equipped with the skills necessary to improve model loading times and resource management in your AI applications. The TensorFlow SavedModel format is a versatile and comprehensive way to serialize your trained models. It encapsulates everything needed for model inference, including the model's architecture, weights, and dependencies. Saved models are platform agnostic, which means they can be used across different environments without modification. This flexibility makes them ideal for deployment in production. A saved model consists of two primary components, the model's architecture and its weights. Additionally, it includes metadata that describes the model version and any specific requirements needed to run the model. Using saved model format ensures compatibility with various TensorFlow services and simplifies the deployment process. It also supports model versioning, which is crucial for maintaining and updating models in production environments. Loading a TensorFlow model can be impeded by several bottlenecks, which can significantly affect the performance of your AI application. Common bottlenecks include slow I/O operations, limited CPU resources, and insufficient memory. These issues can lead to longer loading times and reduced system performance. To effectively optimize model loading, it's crucial first to identify these bottlenecks. Profiling tools like TensorBoard or custom logging can help trace the model loading process and pinpoint where delays occur. Analyzing CPU and memory usage during loading can also reveal resource constraints. Understanding the nature of these bottlenecks allows you to implement targeted optimizations, such as optimizing data storage formats, using efficient data pipelines, or upgrading hardware resources. Reducing the time it takes to load a TensorFlow model is crucial for maintaining a responsive application. One effective strategy is to preload and cache models in memory, which can significantly reduce loading times for frequently accessed models. Optimizing data storage formats, such as using TF record files, can also minimize I/O operations. Additionally, reducing the model's size through techniques like model pruning or quantization can decrease loading time and memory usage. Parallel loading strategies, where parts of the model are loaded simultaneously, can further enhance loading efficiency. Lastly, leveraging cloud-based solutions can offload heavy computation and storage tasks, allowing for faster and more scalable model loading.
The TF.data API in TensorFlow is a powerful tool for building efficient data pipelines. It allows for the seamless integration of data preprocessing and model loading, which is essential for handling large datasets. By using the TF.data API, you can create pipelines that load data in parallel, preprocess it on the fly, and cache intermediate results to optimize performance. This API supports a variety of data transformation techniques, such as shuffling, batching, and mapping functions, which can be applied to your dataset before feeding it into the model. Integrating TF.data with model loading reduces I/O bottlenecks and improves overall throughput, making it an invaluable tool in production environments.
Lazy loading is a technique that defers the loading of a model or its components until they are actually needed. This approach can significantly reduce the initial memory footprint and improve the responsiveness of your application. In a TensorFlow context, lazy loading involves loading parts of the model as required, rather than loading the entire model at once. This can be achieved by structuring your model to load specific layers or components on demand. Implementing lazy loading requires careful design of the model's architecture and an understanding of the application's usage patterns. By deferring unnecessary computations and data transfers, lazy loading improves resource utilization and can lead to more efficient AI systems in production.
TensorFlow Lite is a lightweight solution for deploying TensorFlow models on mobile and edge devices. It is designed to execute models efficiently in environments with limited computational resources. TensorFlow Lite achieves this by converting TensorFlow models into a compact format that optimizes performance and reduces the model size. The conversion process involves quantizing the model, which can significantly reduce the memory and processing requirements without substantial loss of accuracy. TensorFlow Lite also supports hardware acceleration, enabling faster execution on compatible devices. This makes it ideal for applications that require real-time inference, such as mobile apps or IoT devices. By leveraging TensorFlow Lite, you can bring AI capabilities to a broader range of devices, expanding the reach and impact of your solutions. Efficient memory management is crucial when loading TensorFlow models to prevent system slowdowns and crashes. Understanding the memory usage patterns during model loading allows you to optimize memory allocation and improve performance. One effective technique is to adjust the batch size, as larger batches can increase memory consumption but may also speed up processing. Striking the right balance is key. Avoiding memory leaks is another critical aspect, as they can lead to escalating memory usage over time. Using tools like TensorFlow Profiler can help monitor memory usage and identify potential issues. By implementing best practices in memory management, you can ensure that your models load efficiently and your system remains stable. Exploring real-world case studies provides valuable insights into how organizations have successfully optimized TensorFlow model loading. These examples showcase various techniques, such as model quantization, parallel loading, and the use of TensorFlow Lite for mobile deployments. Companies have reported significant improvements in loading times and reduced resource usage, leading to enhanced application performance and scalability. By analyzing these case studies, we can identify common strategies and best practices that can be applied to our own projects. Additionally, these examples highlight the evolving nature of model loading optimization and the potential for future innovations in this area. Learning from real-world implementations can inspire new approaches and help us stay ahead in the rapidly advancing field of AI deployment.
In conclusion, optimizing TensorFlow model loading is a critical aspect of deploying responsive and scalable AI solutions. Throughout this video, we've explored a variety of techniques, from understanding the TensorFlow SavedModel format to implementing lazy loading and leveraging TensorFlow Lite for mobile and edge devices. Efficient model loading not only enhances performance but also ensures that your applications can scale to meet increasing demands. As you apply these skills, consider the specific needs of your production environment and continue to explore new advancements in model optimization. Thank you for joining us, and we hope you feel empowered to enhance your AI deployments with efficient model loading strategies.